Hello, I am Attila and I will be presenting computational exploration of finite semigroupoids, which is a joint work with my long-term collaborator Christopher Nehani from University of Waterloo, which place is a partner university to AIU. So this is a short and easy talk, a shorter version than the one given at the 2025 ICFP Splash Miniconren workshop. If you want to see that includes code as well, then you can use this link with the timestamp to the recording. Okay, so the plan here, I will talk about computational exploration. So what is that idea? And then, well, it's like I show an example of semigroupoids. Those are the objects we are studying. And then I will tell you how we used enumeration and classification techniques using a relational search algorithms. Okay. So, first of all, what is this idea of computational exploration? And that's basically that we are writing computer programs for epistemological purposes. That is to understand something. So now we can think about the levels of understanding. And the first level is that, you know, when I say I heard about it, okay, so I understand it to some level. But that's a totally different thing than when I can say that I did it myself. Yet a next higher level of understanding when it's like when I explained it to someone. And according to this classification, it's like the highest level is that when I wrote a program to do that, and that is I explained it to a computer. And perhaps between the level 3 and 4, we can put writing in a natural language. So it's like it's a little bit easier because it's more forgiving, but it's sort of the same idea. So that's okay. What does it mean as epistemological purposes? So we have this common pattern of writing programs where when you want to solve a problem by using a computer program, then the first version that works is usually very long, convoluted, and unnecessarily complicated. So, well, it's like often if you work in the industry, then it's like, well, it's working, so you just ship it and stays like that. So that is a partial explanation why we sometimes have not too good quality software. But if you have the sort of the academic luxury that you can continue thinking about the solution and look at it again and critically reevaluate it, and then you can rewrite it, then you can make it better. And after a couple of iterations of this rewriting step, the final version is usually very short, elegant, and efficient. So it has all the good properties. So the question is, why cannot we write the last version first? So that would be like the ultimate way of writing computer programs. Well, the problem is because we do not understand the underlying problem. Creating the first version is the learning process itself. Okay, so that's why we cannot see the easy way of doing it because we are not 100% sure what to do exactly. So that's why for us, the AI tools for coding are totally irrelevant, because if someone else does that for us, then it's like we don't understand anything. We didn't learn anything. Even if we ask for an explanation, then we are still stuck at level 1 of understanding. Well, we heard about it. Someone else explained it to us. And also you might argue that, if the specification of what needs to be coded is complete in the first place, then you don't have these iterations. While if you have a complete specification in the beginning, which describes all the exceptional cases and everything, that means that you already fully understood the problem, and it's just the matter of translating from the description, the specification language to the actual programming language. So there seems to be no shortcut in this one. So yeah, what do we study? What do we want to understand? And that is sort of it's a bit of a twisted story, because while we want to understand computation itself, we can say by an analogy that we are doing the particle physics of computation. So there is a bit of a self-reference here. We study computation by using computational tools. Here's a link to a preprint paper if you are interested in the details. But well, let's move on and let's have an example of a finite semigroupoid. So normally in mathematics we would start with the abstract definition, but since this is a very short introductory video, let's have an example. Okay, so basically a finite semigroupoid is just we have a bunch of objects, these the sigma and tau, which we also call them types, and we have arrows between them. And how do they behave? Well, they can be composed. So if I compose A with a C, let's see, what do I get? I compose A with C. Oh, that's going to be just C itself. If I compose, well, here are the equational representation. If I compose B with B, I get A. B with D, I get E. And you see, it's like I said that sigma and tau behaves like types, because it's like it says that this computation AB, AA, BC, FF is a valid one, so we can always compose, while ACB is not valid because B is not composable with C. If you look at it, it's like after C, yeah, it's like can we compose it with B? Well, it's there is nothing there in the composition table, so that shows that. Well, here's just sort of like a homomorphic image of that. It's a simplified image where we just do this with the types, but that's not the key point here. So that's how you can think about a semigroupoid. It's just arrows and a bit of some rules around how you can compose the arrows. And here's a different representation of that. It's getting closer to actual computation. So now we have states 0 and 1 here, and 0 prime and 1 prime here. And if I keep switching between, so you realize that while the sigma becomes x, this state set, and tau becomes y here, and it's basically this just describes that how the arrows corresponds to actual state transitions there. So that's a more concrete representation. So of course I can give you the official definition, and if you know category theory, then it's like, oh, this looks very familiar, except that we don't insist on having the identity morphisms for all objects. But for our purposes here, all I want to do is to draw your attention to the rules of associativity. Okay, so that's like if we have 3 arrows in a row and they can be composed, then it's like the order how we do the composition does not matter, because that's what we are going to use. So what are the questions we ask? And it's like, first, what are the finite semigroupoids? So that's the enumeration problem, when you want to start with the smallest one and simplest one, and then it's like sort of see what do we have. And in order to do that, we also have to answer the question that whether 2 semigroupoids are the same or similar. That's the isomorphism problem, or the problem of creating homomorphisms. And as I hinted before, we are interested in different representations. So we have the abstract representation, which is just a composition table, or we have an actual transformation representation where we have states and then we have state transitions between them. So we developed a software package for that using the closure language, which is actually taught here at AIU, and using a very specific library is the core.logic. That's for logic programming, and all the code that is described in the paper can be found in this folder in this open source software package. So what's so special about this core.logic programming? So it's like, well, we have sort of a different way of thinking. Often when we do computer programming, it's functional thinking. You have input and you produce an output. Like, okay, here's this cool mathematics example. Is the exponential function f of x equals to the x. So if you have input 3, then the output is 8 because 2 to the power 3 equals 8. So if you think about it, it's like, oh, in this case, we can actually run the program backwards. It's the so-called inverse function. So if the input is 8 and then the output is 3, because the base 2 logarithm of 8 is 3. So now in relational thinking, we just get rid of this input-output thinking. We say that only what we have 3 numbers in a certain relationship. And the way we do programming is that if one of them or more than one are missing, then we can find the suitable values for them, or actually the computer can automatically find suitable values for them. So in the case of 2, 3, 8, well, nothing is missing, so it's like there is nothing to be found, and it's like, well, if the first one is missing, then we know by the relationship that it has to be 2, and if the last one is 1, then we know that it has to be exponent should be 0, so we actually have infinitely many solutions. But we can have finitely many solutions, more than one as well. So for example, 64 is 2 to the power 6, or 8 to the power 2. And if all of them are missing, then we have infinitely many solutions. When the relationship is satisfied, a to the power b equals c. So how did we use that? Well, it's the same trick for semigroupoid enumeration. So the functional thinking is that, okay, what's the input? The input is the composition table, and you can write a very simple program to check whether the table is associative or not. But what we do the relational thinking. We say that it's like, oh, we say that the output value is true, and now we want to have all the inputs. So all the composition tables that are associative. So, well, to oversimplify the story, that's sort of what we did. And among other results, we produced this table, which is just the number of distinct, so really different semigroupoids for a given number of objects, dots, and a given number of arrows. So for example, if you have 4 objects, 4 types, and let's say you have 5 arrows, then you can have like 34 distinct semigroupoids of that type. So yeah, the table goes on. It's not too far because this is a lot of computation, a lot of search for doing that. But it's like, if you're interested in the details or in the full table, I would ask you to check the actual paper. Other than that, we are finished here. Thank you very much for your kind attention.